So first of all, let me show you a little bit what I want to do in terms of homework problem. So okay. Okay. So basically, the first thing is that I will review your example with the discriminant.
Mm-hmm.
Oh, wait. For some reason, it doesn't let me to draw. Oh. It doesn't let me. Oh, no, it does let me to draw. Huh. Yeah, it doesn't. Okay, so first we just do example with the discriminant. So you put here like data A, B, C, and you are getting back valid. So we put like data with valid, and we have like a busy signal, and we don't expect this to be pipelined because no, with the discriminant you can make it pipelined actually, because with discriminant there is no square root and there is no division. So first we need to make a pipeline version of discriminant, but discriminant pipeline may have very long latency. For this reason, it can be with a FIFO. So with the wait. No, it's not. It's not going to have a very long. It's actually a short latency because we have only 2 clock cycles for. We have 2 clock cycles for multiplication and addition, and we don't have anything else for discriminant. So for discriminant pipeline latency will be like 5 clock cycles or something, right?
Mm-hmm.
Yeah. So let's.
Yeah.
Mhm.
So the multiplication block using the Wally CPU takes about 1, 2, 3, 4, 4 clock cycles to give the result.
Is it 4? Did you test it?
1, 2, 3. Third one, yeah. Third.
Yeah.
I see
So this
3.
has a three clock cycles. So if
2,
you put
3. Yeah.
if you put 2 multipliers running in parallel, you do b square and you do AC, and then you multiply by 4. So you
Mm-hmm.
have like 3 clock cycles, and then 3 more clock cycles. So it's 6 and plus
6,
7
yeah.
and plus 3 more. So 10 clock cycles.
Mm-hmm.
Then you like add everything. So you have
Yeah.
like 10 clock cycles pipeline. Yeah. So we can actually put a discriminant example with all the variants we talked before, which is with FIFO after it and credit-based flow control. Yeah,
Okay.
but but this is not that high priority. The high priority task is to make a quadratic equation a finite state machine,
Okay.
and then once we do it, we instantiate. So like you see, if you do it using finite state machine, this goes through this block with a very long very long latency. So the latency is I can tell you what the latency is because I have this book. Oh, wait, we need not FU. FU, it's a fetch unit. We need FPU. Where is the yeah, floating point? Yeah. So if you go through so according to this book, this division and square root can take long number of cycles, in some variants even more than 100 clock cycles.
Oh, okay.
So from like 10 to 100, something like this.
Mm-hmm.
Yeah. So just a moment. Okay. Yeah. So you see that if you look into so if you look into division, so if you find like yeah, division and square root. So in this book there is a table, but you can figure it out experimentally, which shows the number of clock cycles consumed by like maximum latency of division and square root. Okay, let's see. And basically, you can balance latency versus clock frequency here.
Mm-hmm.
And this is one exercise I also want students to do. So, like, I don't want to students to learn all these details of floating point, but I want them to run exercises with synthesis where they put different variants and see number of clock cycles and maximum frequency.
Mm-hmm.
So just a second. So where is the latency? I saw a table here. Yeah, so like all those mathematical details, I don't want students to see it unless they really want. Because it's just like a lot of stuff, and for majority of people it's not relevant. Where's this table? Latency conversion. You see, so this book is coming on market, I think, like in March.
Mm-hmm.
Where's latency? So latency. Oh, I remember it was F4. Remember that he mentioned it in here division. Yes, so like I will find it eventually, but you can just experimentally find the latency of division and latency of square root.
Mm-hmm.
Let's search for latency. To reduce latency. So this has somewhere table of latency of different operations. Divider latency. Quotient conversion. Early termination. Yeah, but my point is that depending on what's strange. I saw it somewhere and I cannot find it now. Divide. Maybe I saw it. Maybe I saw it on their website.
Mm-hmm.
Vision. Yeah, well, maybe like I saw it on their website, but it doesn't matter because you can figure it out experimentally.
Mm-hmm.
So my point is that between request and getting solution to like quadratic equation, it can easily take you from like tens to like 200 cycles, right?
Mm-hmm.
So now we need to create example where we instantiate n such blocks, and then we have a bunch of requests coming with like valid ready interface for like ABC.
Okay.
And then we have here we have here kind of arbiter, not like arbiter, this one sequencer, which put first request to this one, then second request to this one, then third request to this one, and so on. And then it is possible that they are coming in different order. So maybe we are getting this first, and this second, and this third. And because they're coming in different order, we may need to put together with each block a liter FIFO where we put ID associated with this request, ID. And then here we need to put some logic which keeps track of the next result. So it keeps counter what next result is supposed to get. And if something is coming from here earlier than from here, it should store it somewhere and wait until result from here is coming. So we have to put here some sort of reorder buffer which just stores results here and then gives them back in order. So this is a very useful micro architecture example. You see? Yeah, but we will go through this. We will go through this like later on, once I review your discriminant and quadratic equation example. Yeah, so we need to make a computing unit which does this. So it's just it splits request to compute roots of quadratic equation to multiple computing blocks, and then it collects back responses and gives them back in order. Yeah. Okay.
And
Yeah.
yeah, those blocks, it's the same quadratic equation blocks,
Yeah,
right?
this is the very same code. So we are using this block as a black box from previous exercise. So each of them are the same quadratic equation blocks. So we have inputs like ABC, values, and we have outputs like x0, x1, and the sign of discriminant. So if sign is negative, it means that we don't have solutions, or we can give back like number of solutions. Is it 0, 1, or 2? And then we collect this and we return from this block. So from the point of view of external observer, this will be a computing block which gives you answers the same way as a small block inside, but it gives like answers with a higher performance. So instead of giving you like answer every like once 100 clock cycles, it gives you answers every like 10, 20 or 30 or 10 clock cycles. Based on number of such blocks instantiated. We can even make it flexible, so they can instantiate like even like 1,000 blocks if they want. And then we can see that this behaves like as a practically pipeline block, so it doesn't have any back pressure with sufficiently large number of such computing subblocks. Yeah,
And the
but
inputs to the, yeah.
Mhm.
Yeah, the question is the inputs will be a bunch of inputs, right? Not just A, B, C, but a bunch of A's, B's, and C that goes into
We
like.
will just do A, B, C every clock cycle, like in
Okay.
like ideal case. So
Uh,
we will have some like a back pressure here in terms of ready, or we can make a credit-based interface.
that's based on the number of quadratic blocks instantiated.
Yeah, yeah. So we can put that we can like accept up to this number,
Mhm.
and so we can just but interface to this large block will be the same if, like as interface to small block.
Okay, yeah, you're serially sending A, B, C. The next clock cycle, you send the next A, B, C, and third, you go on.
Yeah, and then like at some moment you start getting equations from another end, and you're getting equations in the same order, and in order to get equations in the same order you need to reorder this to reorder data in this block.
Okay. So the question is, let's say for example, the first block takes 100 nanoseconds or 100 clock cycles, and the
Yeah,
second takes 50 clock cycles. So if you're
yeah.
reordering, the output should be the first block's equation. The second,
So so
so
what
it,
happens is that you get answer from this block, and this
yeah.
answer is stored in some like table, and this
Hmm.
table is indexed by ID, and you
Hmm.
pass this ID using this FIFO on the side of this block.
Hmm.
Okay,
Yeah,
so
that's
you're
fine.
using this ID as an index, so you're stored
Yeah.
in some place here. At the same time, you maintain here pointer to the next item to put outside, and you wait here until this slot is occupied. So those other slots can be occupied out of order, but you wait until first will give you a response. So even if second and third will give you response earlier, you wait for the first one. And once you get a response from first one, you move this pointer to next slot, and you output this first one to like outside.
Yeah, that's the question. So let's say, for example, I have the first one gives the output at 100 clock cycle.
Yeah.
So up until 100 clock cycle, I won't be able to see the output
Yes,
for the first
exactly.
one. So let's say
Yeah, yeah,
if
yeah.
my first one, I get the output at 50th clock cycle, and the second one, I get the output at 100th clock cycle. So at 50th clock cycle, my FIFO will receive and I'll be able to see the output. And the next output will be after 50th clock cycle from that output, right?
Yeah. So like if like suppose first one took you like 50 clock cycles. So like
Hmm.
suppose this one was doing this like 50 clock cycles, and this one like was doing also 50 clock cycles. So you start in one, and this takes 50 clock cycles, and then on next clock cycle you start with two, and this
Yes,
also took 50 clock cycles. So basically, you will get a result of first one in a
the
clock
next clock
cycle
cycle.
50, and
Yeah.
second one of clock cycle 51.
Yeah, but what if the second one is at 100th clock cycle?
Yeah, if second one is 100 clock cycles, then
Then I
you
have to
will
wait.
get on like on 100 like 100
Clock
of clock cycle. Yeah, but if
Okay.
suppose the first one is 100 clock cycles and
Mhm.
second one is 50 clock cycles, then you get first one in 100 clock cycles and second one in 101 clock cycle.
One, yes.
Yes,
Yeah.
in 101 clock cycles. So like ordering. So you have to maintain. Yeah. So you have to maintain order.
Mm-hmm.
You have to maintain order, and we need to create microarchitecture structure to maintain order, but latencies will vary. But like on average, you will use less clock cycles than if you use only one block.
Mm-hmm. Yes.
Okay. So did you create already solution for discriminants? So can you make pull request for that repository or not yet?
I've not yet made a pull request. I'll go ahead and make
Okay.
that now.
Yeah.
And
So make pull request and we'll do some additional review. Yeah.
yeah, and I've had a
Okay.
few lines in the test bench to send the input as nan and infinity just to check. I can remove that for now. That is there. Once you verify it, I can remove those lines. Or do you want me
Yeah.
to?
This is so just put pull request and we sit down and do review. So
Okay.
somewhere like during the coming week.
Okay. Sure.
Yeah. So we need to do that, then we need to do block computing quadratic equations, then we need to do this structure with the multiple blocks.
Yeah.
Okay, this is fine. Hi.
Yeah.
Yeah. So like are you here first time? Yeah, okay. So can you tell like about yourself a little bit?
Sure. So my name is Pratik. I just moved to Bay Area for a new job. So
Okay.
I'm very interested in architecture. So I was looking for groups like this. So I came across this on Meetup.
Okay. So, but what? So what did you do so far? So, what is your like
So
experience?
I'm currently in the Questa simulator team.
In question. Okay.
Yeah,
Okay.
in their
In a
performance.
mental graphics,
Yeah,
Siemens
in
CDA.
Siemens, yeah. So
Interesting.
I work with system Verilog, mostly specification and performance, compiler performance of the Questa sim.
Okay.
But I want to be on like the hardware side.
So you want to learn the basics of design, right?
No, I know basics of out of order design and like accelerator design.
Okay.
So I wanted to like, contribute more towards.
Hmm?
I wanted to contribute more and learn more towards.
Okay. Good. So you can actually do like micro architecture examples also. Yeah. So basically, what we do is that some part of this group is meeting here and some part just through like online.
Sure.
And we are creating like a series of different examples.
Yeah.
And some of those examples run on FPGA boards.
Yeah.
And some of those examples run in simulation.
Yeah.
So we have like a thing called like system Verilog homework. So if you look to the website, you can actually look at it. Yeah. So just go to Verilog Meetup. Yeah, and now scroll down. Go to the main. So yeah, scroll down. Yeah, so go to self-educating and educating others. Yeah, so now go down. Here. So you go to this GitHub repository. So, but what exactly, what part are you doing in a Quest team? Is it a simulation engine or something outside, or?
So performance, compiler performance.
Ah,
How to compile fastly. And before that, I was in cache design. Cache
in case, yeah, but which company did you work for? Cache?
I in laboratory.
Huh?
In a lab.
So like using like in the university, right?
Yes.
Okay, good. Yeah, okay, good. Yeah, so send me like me an email. I will put you on the list of yeah. So just send the mail at yuri@pancho.com.
Okay.
So let me write it down somewhere. or you can connect on LinkedIn.
I think I'm connected.
Okay, yeah, but just send me email so like I put it into yeah. So YURI. Yeah. Yeah, I was actually working in a mentor graphics, but very long time ago.
Okay.
In Oregon, yeah, doing.
I work in Fremont office.
Yes, but like in Oregon, this was doing seamless co-verification environments. This was very, very long time ago.
I'm part of design verification technology,
Uh-huh.
but I don't do verification.
Yeah.
I just look at UVM framework in Questa simulator
Uh-huh.
and different optimization because like they do background optimization on design, right? So sometimes like the designs break, the RTL breaks because of those optimization and performance. So let's say a design is taking 15 hours, like an Intel SoC is taking 15 hours. So how to do it in like 3 or 4 using optimization, using Questa simulator. So that right now I just started, so it's like very that kind of, yeah.
No. Okay, so yeah, Yuri at panchul.com. YURI
Yeah.
at PANCHUL.com. Yeah. Okay. Okay, so just send me email. Yeah. So basically, this system Verilog homework. This starts from like absolutely zero.
Yeah.
So and it's all using Icarus Verilog. But by the way, you're welcome to make a Questa script there. To put this will should be very easy, and this very easy to just because this is all run using bash scripts.
Okay.
So if you like just clone this repo, there is a bash script called run all exercise, and it gives you pass or fail. So you can put the support for Questa.
Okay.
So you can so go up, no, go up. Yeah, so if you go here to, let's say let's go to 0-1 combinational logic. So you see, this has bunch of like individual tests, and this has scripted then, which is called run Linux Mac or run Windows. And if you look inside, this redirects you to script in different place. But if you go to that place, if you go to scripts here, so go to system homework, and then you go to scripts, and this run Linux Mac, yeah. So if you go here, there is a script here which runs Icarus Verilog, and you can put here script which runs Questa, so which is like useful addition because there are like tons of people who use Questa in like especially educational edition. But so here, like in those exercises, it starts from like very zero, and then it goes to like FSMs, pipelines, credit-based flow control, and we want to put here some more exercises. And for some of these exercises, we are using pieces of open project called the Valley, which is the open hardware GitHub repository. And professor who created this Valley CPU, David Harris, he's also like author of textbook Digital Design and Computer Architecture. Yeah.
Oh, that Harris and Harris.
Yeah, Harris and Harris. So he is then now writing another book, and we got his CPU and just got FPU from it, and we are trying to build student examples by combining FPU pieces. So like adders, multipliers, square root, division, and so on.
Oh, like floating point unit.
Yeah, floating point unit.
Is this out of order or like?
So his CPU is a static pipelines, like 5-stage pipeline, but it has TLBMMU, and this has caches, and this has like a few. So it can run Linux.
Yeah.
And it can they have synthesis script for Synopsys, and it can run on FPGA as well. So, but we are actually using it in a different way. We are getting FPU, getting blocks from this FPU and combine them together to form student exercises.
Okay.
So something like use this to compute like a quadratic equation roots.
Yeah.
And you can do it with a few blocks and make it small area, or you can do with a larger area. So if you instantiate multiple instances of it,
Yeah.
you can just send every new things every clock cycle on different instances, then getting back response and improve performance. So basically, like I work in Samsung, so like I do like interview questions for like people on like pipelines and FIFOs and stuff, and and basically those like examples, like some of those examples, they are following type of things we have like during job interview, because apparently many students, for instance, when I ask them to build like something which compute formula with dependencies. So something like uh, square root of a plus like under square root of b plus square root of c, uh, and to accept argument every clock cycle. So like ABC every clock cycle. Huh?
Initialization interval is one. Like the pipeline should keep going.
Yeah, so pipeline should keep going, and so many students, when I ask them this question, they just put three square root blocks one after another. But the problem is that by the time you compute square root of c, then like b and a are gone.
Yeah.
So and then they don't know where to put them, and then ask them, but you were studying like FIFOs and shift registers, just delay arguments. But apparently many fresh graduate students don't get it. Like initially, then they can figure it out. So as did you study like FIFO, and then they show structure with this block at FIFO. So yeah, and you have a bunch of examples like that. But if you want to build the whole library of them,
Which one would be better? Like if you put shift registers to delay other inputs, or you use one block and do it in 3 cycles by using an accumulator.
The problem is that if you do it in three, so the problem is that if you do it in 3 cycles, you need to stall. You need to put back pressure on input, and so you will reduce bandwidth.
Yeah.
So yeah, you can implement it with the multiple with the long latency, but in this case you cannot do this each clock cycle. You can do this only after number of clock cycles, but you can have small area. But if you need to do it each clock cycle, you need to put additional 5 for shift
To make it non
shift register, yeah, to make it non-blocking. So you have a bunch of examples like this, and we do need to create examples of this nature. But before we can, plus I also want to put examples for like standard like scoreboarding with like CDC, Tomasul, and so on. But those examples should work both in simulation and on FPGA board, because we like support like more than 30 FPGA boards.
Yeah.
And this all should be work on like FPGA boards as well. So, but before I ask you to do one of those things, you can just get this homework and just go through like existing things. And once you go through existing things, and they will do some review. So then we will make some common style to work on the next exercise. Yeah, but basically to do this, all you do is you clone a repository, you get Icarus Verilog, just using like git apt-get iVerilog, and you run the script, and that's it. Yeah, so this is like a first step. And like also, because it all has to be compatible with FPGA boards.
Yeah.
Like I also show you how to work with FPGA boards.
Yeah.
So what is your experience with FPGA boards?
I have experience with Xilinx data center cards
Mhm.
and HBM cards.
Yeah.
high bandwidth memory because I was working in cache design. So
Yeah.
I synthesized pipeline caches on FPGAs.
Okay, okay. Yeah, you see, here we have just a simplistic push button synthesis. So we have just
I
just
use
like
Vivado.
huh?
I use Vivado for synthesis.
Yeah. So we have scripts which, based on board number, use either Vivado or Quartus Altera or Govin or like open source. And basically, for such exercise, you can even let me give you the board. You can even use board which, let me show you our, yeah, so he can show you this board. And maybe like another thing what you can do right away is that, yeah, you see, such thing costs just $25.
Yeah.
but this has enough
one is
to run microarchitecture. This is a Govin.
Okay. Oh,
Yeah.
is it like something like lattice boards?
No, this is not Lattice. Lattice is a competitor to Govin. Govin is a new Chinese company.
Yeah.
Which makes this uh, uh, which makes this new boards. So yeah, maybe like right now you can show to him how to run examples, and they will talk with other people. So yeah, so just like demonstrate him like running these examples, and while like I will talk with other people. Okay, so now. Oh, wait. Where is, okay, where is Jorge? I need to get Jorge, just a second. Okay, so now Pratik, oh, so you're here like you Zoom. Okay, so Evgeny, so I noticed you joined. So what did you try to learn so far?
So I'm doing exercises. I'm still on stage 0. Looks like Harris doesn't have the explanation for those cases. So I just got the book for Verilog, System Verilog. I'm just reading System Verilog.
Okay. Yeah, so
So,
Harris actually does have something about cases.
but it's
Just a
kind
second.
of all in.
It's a very sketchy, yeah. Yes, I agree.
Yeah.
Yeah, so you need to get in this case second book, and you also can download standards, so you can read from the standard. So if you just
I can tell you which one I got. Just
okay, you can show me. So you can share the screen and show book you got.
Oh, that's in. Oh no, it's on my iPad. Just can quickly open. I just can give you the name. I think you know the name.
Link, yeah.
Okay.
Just put link in chat or name in chat.
It's Navbi is. Oops. Oh, Navabi Zainalabidin. Okay, yeah.
Navabi, but
Yes.
Navabi is but Navabi is a very old book. Just a second, or maybe
It's
he created some new book.
embedded core design with FPG. Maybe 2016.
Okay, let's see. Navabi.
2007. No, 2007. Yeah, 2007.
Navabi, and I think this is not the first edition because Navabi was even in 90s.
Okay. Okay. So I have a Thompson, I think, also Thompson that you recommended.
Yes. Thompson
So,
is a better.
so Thompson's better. I just started. Mhm.
But I'm talking about a new Thompson. So can you show which Thompson you have?
Oh, probably. I'm not. I have to find it. I can send you. Yeah, Navabi. Yeah,
So you're talking about this one, yeah, but this is second edition. So first edition is like all there.
So
They're like all fine, but I don't think that Novabi has system Verilog. But
yes.
it doesn't really matter what you read at this point, as long as you get all the syntax. So did you get like a Donald Thomas like this one, or did you get the earlier one? Because this also has multiple books. And one
Okay,
of them is a book from year 1990.
So Thompson should be the latest. Yeah, Thompson.
Yeah, Donald Thomas.
Thomas. Yes, Donald Thomas. I have to.
So which exactly book do you have, Donald Thomas?
Probably it's old. Looks like.
If it's old, it has like old syntax. So I don't recommend old syntax.
Okay, see. Okay, let me see what they have here locally. Probably I'll get the new one. So you say it's on Amazon, right? I can just get it.
Yeah, but on Amazon, yeah, it's on Amazon. But on Amazon there are multiple rules. I have all the links on this web post, self-education and educating others. So I will just share it.
Mm-hmm. Yes. Okay. Yeah, I see.
So if you go
2016, yeah, Donald Thomas.
yeah, 2016 is okay.
Okay.
Yeah, one thing that it shouldn't be like 1990 or like 1999, because that one uses older version of the language.
Mm-hmm.
Yeah, so but Donald Thomas 2016 is okay. So just go to this place and also get standard for system Verilog. So get this standard, and I do think that Harris and Harris have like a case statement, but you need to follow standard and go through exercises. Just once you get the first set of exercises, then you're in good shape. Just send me for review the first set of exercises.
Okay. Because they pass. Okay. So even though they pass, so okay, yeah, I can send. Yeah. No problem.
Yeah. Because even if they pass, it still can have some errors. So that pass does not guarantee anything.
They are
Because
just
in Verilog, the problem with Verilog that first of all, Verilog is not like one language, but more like 5 languages in one.
Yeah.
But second is that not all constructs are synthesizable. Not all constructs can be put into hardware. So you have synthesizable subset and simulatable subset.
Oh, okay. So I see. Yeah.
Yeah.
Okay.
So,
yeah.
Okay, so you can to do this, and also I recommend to do exercises with the FPGA board in parallel to it.
So yeah, I loaded Govin IDE, but I think I decided first to go through those static, let's say just test only exercises first,
I
because
see
I'm new to it.
simulation exercise.
Yeah.
Okay, this is fine. Just to learn syntax.
For Go, yeah. Because for
Yeah,
Govin
either
it's
way is okay. Yeah.
okay. Yeah.
Okay, so now let me catch Jorge, because I needed to talk to him about seminars in Mexico. Okay. Okay. One. Okay. Yes. Yeah, so because we are planning seminars in Mexico, now I need to get Jorge's Havala, who initially joined call, but now he went out, so I need to catch him back and discuss it. Because we have some like elementary exercises for that. Okay. Let me get a hold of him. Okay, so Kieran, Evgeny, and Pratik, everybody have some like tasks. If you have some questions, you can ask me. And now I will get Jorge and discuss Mexican exercises with him, and we'll do some like activities here.
No, I don't have any questions.
Okay. Yes,
Nothing.
Kieran, do you have any questions right now?
No, nothing now, Yuri.
Yeah,
I
if
just
you
think
don't,
that
then we can finish call and I will just do something here locally.
yeah, sure.
Yeah. Okay. So thank you, everybody. Yeah.
Okay, thanks.
Bye. Yeah.